fast montage of mobile apps, websites, banking software dashboards, code scrolling in background. Behind every successful software product is a structured process called SDLC. In this video, we will explain what SDLC is, why it matters, and its main phases. The software development life cycle is a systematic process used to design, build, test, and maintain. It helps deliver software on time, within budget, and with high quality. SDLC is important for reducing risks and improving efficiency. It improves planning, reduces errors, and ensures better software quality. Now, let's explore the main phases of SDLC. The first phase is requirement analysis. Developers gather and analyze user needs and expectations. The second phase is system design, where the system structure is planned. This phase defines architecture, database design, and user interfaces. Developers convert the design into a working software system. The next phase is testing, where errors and bugs are identified. Testing ensures the software meets requirements and performs correctly. After testing, the software is deployed for real users. This is when the system becomes available in a real environment. The final phase is maintenance. It includes updates, bug fixes, performance improvements, and security patches. SDLC consists of requirement analysis, design, implementation, testing, deployment, and maintenance. Understanding SDLC is essential for every IT and computer science student.
So this developer's journey, that's the exact roadmap we're going to follow today. And as we do, you're going to see something really cool happen. All those seemingly random exam topics, programming, databases, networking, they're not random at all. They're just logical stops on this one big adventure. Okay, so first up on our journey, the plan. Think about it like this. You wouldn't build a skyscraper without a blueprint, would you? Of course not. It'd be chaos. Well, software is exactly the same. You need a solid roadmap. And this isn't just some nice-to-have suggestion. It's the structured plan that takes an idea from total chaos to a finished product. And yeah, in the dev world, this plan has an official name. And that name is the Software Development Lifecycle, or SDLC for short. Just think of it as the big picture map for our entire journey. It's the model we use to make sure we're building good, high-quality software without wasting a ton of time. It really is the framework that holds everything else together. So, what does this SDLC map actually look like? Well, it breaks down the whole massive process into a super logical flow. Step 1, you figure out exactly what problem you're trying to solve. Then you dig into the specific requirements. After that, you come up with your game plan, the algorithm. Then you write the code, test the heck out of it to find all the bugs, and finally, you document everything so someone else can pick it up later. See? A logical flow. But not every project takes the exact same road. There are different ways to follow this map. For example, you've got the waterfall model. This one's super strict and step-by-step. You have to finish one phase completely, 100%, before you can even think about starting the next. It's like building a house one floor at a time. Then you've got the iterative model. This is totally different. It's more like building with Legos. You build and refine the software in small, repeatable chunks or cycles. All right, so we've got our roadmap. We know which path we're taking. Now it's time to actually build something. This is where we switch gears from planning to actually creating. And it all begins with the fundamental building blocks of logic. And hold on, before you even think about typing a single line of code, you need an algorithm. Seriously, this is the absolute heart of problem solving. It's the step-by-step recipe, the exact instructions your computer is going to follow to solve that problem we defined way back at the beginning. Now, to turn that recipe into clean, organized, and manageable code, we often use a powerful style or philosophy called Object-Oriented Programming, OOP. And OOP stands on 4 main pillars. You've got inheritance, which is all about reusing code you've already written. Polymorphism, which is a fancy word for using one thing in many different ways. Encapsulation, which is like putting your data and the functions that use it into a neat little box. And finally, abstraction, which is all about hiding the complicated, messy stuff so you can focus on what's important. Okay, so you've written all this beautiful OOP code. But how does the computer, which only speaks in ones and zeros, actually understand it? Well, it needs a translator. And there are 2 main types. First, you have a compiler. A compiler is like a book translator. It reads your entire program and translates the whole thing into machine code at once. Then you have an interpreter. An interpreter is more like a live translator at a conference. It goes through your code line by line, translating and running it as it goes. Okay, let's recap. Our program can now think. It can follow instructions. That's awesome, but what happens when the user closes it? Where does all that important information go? You know, the user accounts, the high scores, the shopping cart items, poof, it's gone. Our application needs a memory. And this isn't a small problem. It's a critical one for any real-world app. I mean, sure, you could just dump everything into simple text files, but that gets messy fast. You'd have the same data copied in a dozen places, things would get out of sync, it would be a total nightmare. No, you need a much smarter, more robust system to manage the application's memory. And that system, my friends, is a database. A proper database management system swoops in and solves all that chaos. It's designed to slash redundant data, make sharing a breeze, keep everything consistent, and give you a super efficient way to find the exact piece of information you need right when you need it. But how do you keep that database from becoming a digital junk drawer? Well, there's a key process for that, and it's called normalization. Think of it as the ultimate tidying up method for your data. It's all about strategically breaking down giant, messy tables into smaller, cleaner, and much more logical ones to cut down on repeated info and just keep things solid. And this tidying process, normalization, follows a set of rules called normal forms. Think of them as levels. First, normal form, or 1NF, is about making sure each piece of data is as small and indivisible as possible. No lists in a single cell. Then, 2NF builds on that and gets rid of certain kinds of redundant data. And finally, 3NF takes it even another step further to clean things up even more. With each step, your data structure gets stronger and more reliable. So you've got this beautifully organized database. How do you actually talk to it? How do you ask it questions or tell it to store new information? Well, you need a language for that. And that universal language is SQL. structured query language. With just a few simple commands like create, select, update, and delete, you have complete control over every piece of data your app could ever need. Okay, let's pause and see where we are. Our application has a blueprint, it has brains, and it has a memory. That's fantastic. But right now, it's basically living on a lonely island, stuck on a single computer. To be really, truly useful, it needs to connect to the outside world. It needs to communicate. And that communication happens over networks. And just like we have rules of the road for cars, networks have rules for data called protocols. The absolute foundational rulebook for the entire internet is called TCP/IP. It's this amazing system that lets any computer break a message into tiny little packets, shoot them across the world, and then have another computer reassemble them perfectly on the other end. It's what makes the internet, well, the internet. Now, within this rulebook, you've got two main communication styles. First, there's TCP. Think of TCP like a phone call. You pick up, you say hello, you establish a connection, and you make sure every single word gets through. It's reliable. Then you have UDP. UDP is more like throwing a bunch of paper airplanes with messages on them. It's way faster, but hey, you can't guarantee every single one is going to make it. That's why we use reliable TCP for stuff like email and speedy UDP for things like live video streaming or online gaming, where a lost packet here and there isn't the end of the world. And when we're talking about web apps, all this communication stuff becomes something you can actually see and interact with. It's all thanks to a stack of technologies working together. You've got HTML, which is like the skeleton. It gives a web page its basic structure. Then CSS comes in. That's the skin, the clothes, the style that makes it look good. And then, working behind the scenes, you have a server-side language like PHP, which acts like the brain, talking to our database to create a unique, dynamic experience for every single person who visits. And there we have it. We've literally gone from a simple idea in someone's head all the way to a dynamic, database-powered application that's connected to the entire world. So now let's just take one final step back and look at the whole incredible journey we just took. You see how it all fits together now? It's a completely logical flow. You start with the blueprint, the SDLC. That blueprint guides the code you write, maybe using principles like OOP. That code needs a memory, which brings us to databases. And finally, that whole application needs to talk to the world, and that's where networking comes in. It all just connects.